Hello. So we'll start with today's session. This is live session 10. So we'll solve today the assignment questions for week 9 and some sample questions for week 10, right? So for the first question, we have to match the following schematics. So for the pin diode, I actually missed one part, I guess. Hmm. So for pin diode is obviously this one, right? For photoconductor, it's this one. For 3 avalanche photodiode, it's 2, this one. And for LEDs, it will be this one because the recombinations are occurring, right? So with this, the last option, which signifies 1 cross to 3, 2 to 4, and 3 to 2, and 4 to 1 is the correct one. So in a photodiode, photo-induced carriers are generated in the what region? So these are generated mainly in the depletion region. Because the width of depletion region increases when the photodiode operates in reverse bias mode, right? So for this reason, the photoinduced carriers are generated in the depletion region. With the next question, when the optical power is incident on a photodiode uh, is 10 microwatts and the responsiveness is 0.8 ampere per watt, the photocurrent generated in is what? So with for this we could do P, which is 0.8 into 10 into 10 to the power minus 6, which is 8 microamperes. This is the formula which we have to do. So this, right? Moving on to the next one. Given below is a schematic diagram of a semiconductor detector. The regions marked 1, 2, 3 denotes what? So for the first part is obviously the depletion region, right? Second one is the avalanche one. And third is the threshold or the minimum field, right? So according to this, we'll get option B for this. For the fifth question, photodiodes are usually operated in reverse bias mode. Reason is what? So according to the assertion, photodiodes are usually operated in the reverse bias mode. It's correct, right? Reason one is what? A strong reverse bias creates a strong electric field in the junction which increases the drift velocity of the carriers, thereby reducing the transit time. So according to reason one, it clearly justifies the strong electric field in junction which increases the full drift velocity of the carriers, thereby reducing the transit time. So it's correct. So reason 2, a strong reverse bias increases the width of the depletion layer, thereby reducing the junction capacitance and improving the response time. This is also correct. So these are all the statements which was discussed by sir in the sessions only. And reason 3 says the increased width of the depletion layer leads to a larger photosensitive area, making it easier, obviously. So these three reasons are correct, and simultaneously these are also the correct explanation for reasoning. So for this, the first option will be the correct one. The quantum efficiency of a photodetector on which the average incident optical power is P naught, such that the average photocurrent is I photon given by what? So eta is current by charge of an electron total incident optical power of photons by energy of photon. So this will be IPH by E giving P naught by HC by lambda, right? So now doing it by P naught into HC by lambda into 1 by E. Okay, so they have not simplified. So according to this, option B will be the correct one, right? Question 7, the responsivity related, right? So R is basically I photon by P naught, which gives us E RE by H mu RP. So RE is what? It's the electron generation rate, and R naught RP is photon incident rate, right? So thus we'll get it as E by H mu of this, which gives us as this lambda mu m 1.24. So with this, option A is the correct one. Question 8. Which of the following statement is true for wavelength 1550 nanometer? A PN photodiode is fabricated from a semiconductor with a band gap of 1.9 electron volt. So what is the principle? It can detect signals whose excitation energy is greater than band gap of photodiode, right? So E is basically Hc by lambda. E is 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8. This is given. So 1550 into 10 to the power minus 9. Now E we will get it as 1.282 into 10 to the power minus 19 joule. For being in electron volt, we have to divide it by 1.6 into your minus 19, thus giving it as 0.801 electron volt. as the energy of the signal is less than the band gap of the energy. Hence, the photodiode will not detect any signal. Right. Now, moving on to the question 9 paragraphs. SI photodiode is operated in reverse bias mode with a load resistance of RL equals to 50 ohms and reverse bias voltage of VR equals to 5 volts. The total equivalent resistance is R equals to RL equals to 50 ohm. The photodetector has a bandwidth of B equals to 150 megahertz. The direct current of the photodetector on its reverse because the values of I naught equals to 10 nanoamperes at T equals to 300 Kelvin. When the photodetector is illuminated with an optical signal of PS equals to 1 milliwatt at lambda equals to 850 nanometer, the photocurrent of IP equals to 411 microampere is generated. So, what is calculate the dark current short noise when photodiode is operated at T equals to 300 Kelvin. So, short noise is given by what? Minus 6 plus 10 into 10 to the power minus 9, 150 into 10 to the power minus 6. Right, I just put the values. By solving this, we'll get it as 1.97 at 10 to the power minus 14. Right, so this is only required. So this will be around 1.97. This is the formula based only. So now with question 10, the thermal noise is given by alpha T equals to 4 kb dB by RL is to 4 into 25.9 into 1 into 10 to the power minus 3 into 1.6 into 10 to the power minus 19 into 150 into 10 to the power 6 by 50. So by solving this, we'll get it as 4.97 into 10 to the power minus 14. This. So this will be 4.97. Question 11. The total noise. Total noise is given by 6.94 10 to the power minus 14. Just the summing of the short noise and the thermal noise. Right? So this will be 6.94. Now moving on with the sample questions for week 10. I have 4 to 5 questions, sample questions for week 10. Sorry. So light at a wavelength of 1550 nanometer propagates through a birefringent medium with a refractive index Ne of 2 and refractive index N0 of 1.5 over a distance of 1 micrometer. The phase retardation experienced by the light is what? So the formula is 2 pi by lambda Ne minus N0 cross D. So by putting the values, we will get it as 2.03 radians. Simple formula based. Now, second one, consider that an EM wave can be represented by this Ex, we have e cos omega t minus kz, Ey is minus e cos omega t minus kz plus 90 degree. Then find the direction of propagation and state of polarization. So as we can see, phi is minus pi by 2, right? So as it is minus pi by 2, this one, we will get it as right circularly polarized, as it is minus pi by 2, and as it is moving, giving us e cos omega t plus kz, it is moving along positive z direction, right? So according to this, option A will be the correct one. So for the next question, which of the following is used as a polarization rotator with a reciprocal nature? So with the given xy components, the x components mainly remains the same, but the y gets flipped, right? So this means the output will be having a pi phase difference. So pi phase difference is mainly given by a half wave plate, which can be used as a polarization rotator, right? So with this, 14B will be the correct one here. And for 15th question, a beam of polarized light passes through a Faraday rotator placed in a magnetic field of 0.1 Tesla and a length of 0.15 meters. If the Wordet constant for the material is 2.5 radian per tm, the polarization rotation of the light after passing through the Faraday rotator is what? So with this, we could get it as theta equals to V multiplied by B multiplied by L, which gives us a 0.04 radians, right? This is the formula basically, and this is the answer. So we'll get it as 0.04 radians, right? Uh, so these were the sample questions week for week 10, and as we had already discussed the assignment questions for week 9. So are you guys facing any problem with the assignments? Like, did the week 9 go well? You guys aren't facing any problem, right, regarding the assignments and all? Okay, so according to this, we can conclude that it's all going fine. So for the next session, we'll continue with the week 10 assignment questions and week 11 sample questions, right? So thank you for joining in. We'll meet next week at the same time where we'll discuss upon those things, right?
Okay, sir.
Okay. So thank you for joining in.